This video is going to be all about I/O pins. You know, those metal things that sticks out of most computer chips. But first I want to recap a little. If you watched the previous videos, you know that what I'm doing here is programming an embedded system, or more specifically a small robot from scratch in the programming language C. So far I've planned the software design and I've set up a way to build a project with Make, and I've also created a Git repository and a workflow to track my changes, as well as a CI system to protect my codebase. I had more to say in this first phase of the project than I anticipated, but that just goes to show that there is more to programming an embedded system than just writing code. But in this video I will finally start tapping those keys to make the hardware do what I want, which is arguably the most fun part of all of this. So getting into it. The robot I'm programming has a small computer inside it, a microcontroller, and that's what I need to program to control it. As with any computer chip, this microcontroller has a group of pins to talk to the outside world. And in some sense, programming this microcontroller is just about making these pins do what we want. Or in other words, these are the eyes, ears, legs and arms of the microcontroller, and without them it would be utterly useless.
How about no arms? No arms or legs is basically how you exist right now, Kevin. You don't do anything.
Exactly what these pins do, how many they are, differ between microcontrollers and how they are configured. And I will get into the details of all of this in this video. But the microcontroller I'm using, the MSP430, has 24 configurable I/O pins, and on my robot the job of these pins is to take the input from the sensors and to output the right signals to the motor drivers driving the motors. On a hardware level, I've already decided what pin should do what, because that's something I had to set when I designed the PCB and connected the microcontroller to the other components on the board. This so-called pin assignment can be found in the schematic I made, which I will refer to in this video. And the main focus here is actually going to be to implement this pin assignment in software. But before I get into that, let's zoom out for a moment again and take a look at the software architecture I presented in the previous video. There are many things I'm going to implement in this video series, so I have to be strategic about the order I implement things in, and I have several reasons for why I'm starting at this end of the software. First of all, the code for the I/O pins is at the bottom of the software stack. And generally it makes sense to implement a software stack from the bottom to the top, because then you can finish and verify each layer of code before moving on to the next one. Another reason for starting at the bottom of the stack close to the hardware is that it lets you verify the hardware sooner, which is technically not something I need to consider here since I've already verified my hardware. But if this was a real project, that would be a more important factor to consider. Because in a real project cycle, you'll want to write the software to verify the hardware as soon as possible, so that you can discover any hardware issues and spin a new board revision. Thirdly, it's a good idea to first implement the things that will help you out during the rest of the development. This means you want to set up any debug facilities early. And one of those facilities that I've got is blinking an LED, which depends on having code to control the I/O pin connected to my test LED. And another such facility is tracing logs to a terminal, which is why the next natural step after I've implemented the code for handling the I/O pins will be to implement the UART driver, which is needed for the console tracing. But more on that in a separate video. I think I made my case, so let's get started. I'm going to implement the I/O handling in two files, io.h and io.c, and fill these with a set of functions, enum, structs and so on for configuring all pins. But as always, I begin by creating a new local Git branch. I then create the two files and put them under the drivers directory and remove the placeholder files I added previously. And also update the make file to include the two files. And then I ran it to make sure that it's still compiled. It didn't, because I had to clean up main.c as well. Once I had done that, then it built fine. I started by sketching out the interface in the header file before implementing the details in the C file, because I like to first get an overview what needs to be implemented. The main thing here is the enum identifying each I/O pin, which is a way for me to name each pin and to have an identifier I can pass as a function argument. And I'm just taking the name straight from the schematic here. And just a reminder, I have a document where I describe some of the conventions I'm following when writing C code, so I won't explain every little code detail in this video. And as I've also mentioned before, while writing the drivers, I'm going to do everything on the development board for the microcontroller, the launchpad, and not on the actual PCB or robot. And I will then move on to the robot once I have the drivers in place and need to bring everything together. And since the microcontroller is the same, that transition should be easy. But there is one important difference between the development board and my robot, and that's the package of the microcontroller. The launchpad only has 16 configurable pins, while the PCB has 24 configurable pins. I will account for this difference in the code by having two sets of IO pins, which I can switch between at compile time using preprocessor directives, that is ifdefs and defines. I know this is kind of ugly, but it will have to do in this case. Anyway, the pins for the PCB are the same as the schematic, but for the launchpad I mark most pins unused for now, and I will just then assign them on a video-to-video basis. And after the enum was in place, I ran make again to make sure that it still compiled, which it did. You will also see me write some to-dos here and there throughout this video. I do that for code sections I will clean up or enhance later, either in this video or in a separate video. They are there to remind myself that this part of the code is not done yet. So moving on to the pin configuration. Most pins on a microcontroller can be configured to some degree. This makes it possible to adapt the microcontroller for different designs and reduces the number of pins required to do so. A pin can typically be configured as General Purpose Input-Output, GPIO, acting as either an output or an input, or it can be muxed or selected to one of the other peripherals inside the microcontroller. For example, in this project some pins will be connected to the I2C, UART, ADC and timer peripheral. In short, peripherals are hardware blocks separate from the CPU, specialized to provide certain functions that the CPU can't provide, or to offload the CPU from doing them. I mean, some of these functions can be realized through bit banging, but that consumes a lot of CPU cycles, so it's preferable to use dedicated hardware blocks for it instead. All pins can't mux to the same set of peripherals, and to know which pin can be selected for what, you have to look in the datasheet of the particular microcontroller. On the MSP430 specifically, all pins can serve as GPIO, but each pin can connect to a different set of peripherals, so while there is some flexibility, during the PCB design stage I had to be careful about how I connected the pins to the other components to be sure the pin could actually serve the function it needed to. Further on, the individual pins are logically grouped into something called ports. On the MSP430, each port contains 8 pins, so on the Launchpad package there are 2 ports, while the microcontroller package on the robot has 3 ports. In general, port size is also something that varies between microcontrollers, but is often the same width as the data bus, so typically 8-bit, 16-bit or 32-bit, because this allows you to interact with each port with one operation. Each port is in turn represented as a set of hardware registers, and these are the registers you write to configure the pins. These registers are mapped into memory, which means from the programming or software point of view, they're just another memory address you can write to and read from, and in turn configuring an IO pin is only a matter of writing the right data to the right memory location. At first sight, this idea of memory map registers can be a bit difficult to wrap your head around, but it's a very fundamental thing to understand when working with microcontrollers and other computer chips for that matter. Because, simply speaking, all code on a microcontroller comes down to writing a value to a register or reading a value from a register. That's how you configure a pin, that's how you configure a peripheral, that's how you disable the watchdog, that's how you change the clock rate, that's practically how you do anything involving the hardware of the microcontroller. And transferring this idea to the code I'm going to write, the bottom of my code stack is going to be all register writes and reads, and that's the important stuff. And very roughly speaking, most of the other code is just decoration on top to make my code more manageable and easier to read. And the set of registers for the IO ports on the MSP430 are the following. And these are of course described in detail in the datasheet, but I will talk about some of them here as well. The address for these registers are also given in the datasheet, but TI, as most vendors do, has provided a header file to save us the tedious effort of having to define these addresses in the code ourselves. These defines are used in the classic Blinky example I showed you in a previous video, and I brought this example back here now in the code, but as a small test function inside the main file, just so that we can see later on when I replace the register defines from TI with my own functions. So the way the direction of the first pin in the Blinky example is set now is like this. And without the defines from the helper header from TI, I would have to look up the address of the register and do something tedious like this instead. So it's obvious that the TI header really helps out here, but I still think it's a bit crude to use the define from TI as is, and would much rather prefer having an abstraction that lets me write something like this instead. And much of this video is going to be about creating this abstraction. So my idea is to have several functions to configure each aspect of a pin. Each function will take the name of the pin as first argument, the enum I defined before, and will take the configuration value as the second argument, which I'm also going to define as enums. This will serve as the interface, and then I will just use or hide the define from TI's helper header inside the implementation file. So I'm still going to use the defines from TI, but I'm going to hide them below the interface that I'm going to be interacting with. So now I'm going to go through each function or register one by one, starting with the select register. This register determines the overall function of the pin, whether it should be muxed to the GPIO circuitry and act as a GPIO input/output, or be connected to one of the internal peripherals or internal hardware blocks. Each pin can take 4 different select values, and there is 2 select registers for each port to represent these 4 values. The first, 00, always select GPIO function, and the other 3 selects one of the alternative functions, and exactly which peripheral they map to will depend on the particular pin. I create an enum to name these values, and then a function that takes the name of the pin as first argument, and this select enum as the second argument. I also created a define here to mark variables as unused to avoid compile errors because of unused variables while developing the code. Note, once you have selected the alternative function for a pin, that's typically all the pin configuration you have to do, and the rest of the configuration is done by writing to the registers for that particular peripheral. Though there are some exceptions to this. For example, the timer peripheral requires the pin direction to also be set, which I will show you later. But overall, the rest of the port registers I will go through now are only relevant when the pin is selected for GPIO. Once again, details like these are explained in the datasheet. The next register, the direction register, sets the pin as output or input. Pretty self-explanatory. If you're driving an LED, you need it to be an output, because then the microcontroller is driving the LED. And if you want to detect whether the pin is high or low, for example a button press, it needs to be an input. In the same fashion, I create another enum and function for this. Then there is a register for enabling and disabling the internal pull-up or pull-down resistor of a pin. This is only applicable when the pin is configured as input, that is, when someone else is supposed to drive the pin. To understand this concept of a pull-up or pull-down resistor, you can imagine having an unconnected input pin. When a pin is not connected to anything, you can't really know whether the pin is high or low. It's floating, and the level may actually vary between high or low depending on the noise. This undeterministic behavior can lead to higher current consumption and unpredictable software. And even when something is connected to the other end, it may not always actively drive the line. So the idea is that we pull the pin up or down with a resistor to get the pin to a known level when it's not driven. And this is typically a large resistor value to limit the current drain. The exact same thing can be achieved with external resistors, but having it internal and configurable inside the microcontroller is more flexible and saves board space. To configure the resistor for a pin, you need to write to not one but 2 registers. One to enable the resistor and another one to select whether it should be pulled up or down. The second register actually serves 2 purposes, because when the pin is not an input and instead an output, it sets the output level. But I reuse the same enum and function for both these cases, but I add comments to clarify this for the resistor case. The 4 registers so far have been registers that are written to. This next register is a register that is read from. The in register or the input register gives the digital input level of the pin when it's configured as GPIO input. So when we read the value 1, it means the pin is high, and when we read the value 0, it means the pin is low. Similarly, I defined an enum and function for this, but here the enum becomes a return value instead of an argument. Besides these registers, there are also interrupt-related port registers, but I will cover them in a separate video. With this code skeleton in place, I prepared a new commit and ran through my usual workflow of formatting the code, running static analysis, and compiling. Added the files, and wrote a commit message, and then pushed the commit to GitHub. I also opened a pull request and looked to see that it passed the CI system. However, I didn't merge it at this point because I wanted to continue working on the same branch throughout this video. I could of course have kept all of the changes in these videos to a single commit, but as I mentioned before, I prefer to chunk up my work into smaller commits. Anyway, moving on. With the interface done, the next thing I had to figure out was how I was going to retrieve the correct register from the function arguments in each function. For example, to select the test LED pin as GPIO, I should be able to call io.select. And inside io.select, this needs to translate to 2 writes to the P1 select registers, since I need to 0 the first bit of both registers to select GPIO. There are some different ways I could go about doing that. The naive and most straightforward approach would be to have a big if or switch statement in each function, something like this. That would work, but it's not very nice. It's verbose and wastes precious flash space, because don't forget, this is a microcontroller and the MSP430 only has 16 kilobytes of read-only memory, so I need to be careful about how I write my code to not run out of flash space. I will talk more about how to analyze this memory in a separate video. I could do better than if and switch statements by being a little creative. The first thing I did was to define another more generic enum. I then assign the values in my other enum to the values in this generic enum. This makes it obvious what pin name each pin mapped to, and I don't need to care about the order of the second enum if I decide to organize them in some other way. There's no overhead in defining additional enums like this in C, because they are essentially just a way to name integers. By default, enums start counting up from 0, and I can use this fact to extract the corresponding port and pin number from each enum value. And the way I do that is by looking at the numbers as bits and use bitwise operations. Because if we have a look at the bit pattern of these enum values, there is a clear pattern. The 3 least significant bits translates to the pin number. So to get the pin number, I can mask the 3 least significant bits, and then I can get the pin bit by shifting value 1 with the pin number. The port number corresponds to the 4th and 5th bit, and there are only 3 ports, so only 2 bits are needed to represent them. So to extract the port number, I can shift and then mask them. Note, trying to be smart or creative about your code is not always a good thing, because it often makes the code less readable, which I think is the case here. But sometimes you have to trade off code readability for performance or space, especially when working on embedded systems with tighter constraints. All in all, I create a couple of defines and write a longer comment to explain the approach. And then I create the functions to extract the port number and pin bit. As you may notice, I inline these functions because they are short and I want to avoid the function call overhead each time they are called. I actually initially wrote them as define macros, but I found that they actually optimize better as inline functions. When it came to the pin, I had all I needed now, because I only needed the pin bit, but when it came to the port register, I actually only had the port number, and extracting the port number is not enough, because what I need is not the port number but the particular port register. Once again, I could solve this with a big switch or if statement to get the particular register. That would be acceptable, I guess, or at least more acceptable than previously. But a neater way to do it is with arrays and array indexing. For example, there are 3 direction registers, 1 for each port. If I put this in order in an array, I can use the port number directly as an index value to get the corresponding register. Note, I must store the address of these registers in the array, and that's why there is an ampersand before the values, because the way TI has defined these is just as regular variables that gets their address assigned during linking. So it doesn't make sense and isn't even valid C code to put the variables directly in the array. I have to get the address of the variables. So I went ahead and defined arrays like these for all registers. Lots of keywords on these arrays. In short, I make them static because they should only be accessible within this compilation unit or this file. I make them volatile to prevent the compiler from optimizing away any accesses to these registers, and I mark the values constant since the addresses to these registers should never change. And finally, I put a big comment on top to explain what I'm doing. With all of this in place, it was then fairly straightforward to implement the functions. First, io.select. This is the special case since there are 2 registers to write to for each select value. I switch on the enum and then set the corresponding bits in the registers. The other functions are similar but simpler. Only 1 register to write to in each one. The functions indeed become cleaner when using array indexing like this, compared to if I were to use switch or if statements to fetch each port register. I hold the port number and pin bit in separate values at the top of each function to save flash space, since I use them several times in every function. And then I added some missing includes and fixed some typos to make the code compile. Finally, I also created a struct to hold the entire configuration for an IO pin, and a function which takes that struct as argument and calls all other functions to let me configure a pin with a single function call. At this point, the code was fairly untested, so to test it, I first rewrote the previous test LED function and instead made it use the io functions that I had just defined. I actually only need to set the direction here since the other registers have the right default values already, but for completion's sake, I use io.configure to configure all registers. I also replaced the delay that was implemented with a for loop with an intrinsic provided by the compiler called delay cycles. I compiled and flashed it and confirmed that it still worked. I also created a separate function to handle the initialization of the microcontroller and put it in a separate file called mcu-init. As always, I put a comment on top of each header with a brief explanation. I moved the stopping of the watchdog into the mcu-init function. I will fill mcu-init with more initialization stuff in the future videos. And then I call mcu-init at top of my test function. And I also had to add the mcu-init file to my make file, as well as fix includes and typos again. Then I moved on to the two bigger test functions that will test all pins. First, one function where I configure all pins as output and in a loop turn all of them on and off. Then I comment out the previous test function, the test LED function, and get the new test function to compile. I flashed it and confirmed that it works by hooking up a logic analyzer and looking at the signals in the software SIGROC. And then a second test function where I instead configure all pins as inputs, except for the first pin which I use to control an LED. I configure the pins as input with a pullup resistor, so by default all pins are driven high. I then loop over each pin and wait for each pin to be pulled low and use the LED as visual cue. That is, it turns on when the pin I'm testing is high and turns off when I pull it low. Once all pins have been tested, the LED just keeps on blinking. So once again, I comment out the other functions to confirm that this third test function worked as well. To test it, I act as the operator and pull each pin down with a strong pulldown resistor one by one in increasing order and look at the LED to see that it turns off and on and blinks at the end. These test functions obviously don't test everything, but I will have to do for now, and if there are any remaining bugs, I will just have to sort them out later. It's not so nice messing up the main.c file with test code like this and to comment out unused code, but I'm leaving it as a to-do to improve on this in another video. I then formatted, CPP checked and committed the new code. I pushed it to the same pull request that I opened before, and yet again I kept the pull request open for the next commit. With io functions in place and knowing that they kind of worked, next it was time to initialize all the pins. Since I know how all of these pins should be configured, and since most pins will have the same configuration throughout the entire run of the application, it makes sense to configure them all in one place at boot. And regardless, it's good practice to explicitly give all pins a default configuration at boot, even if some of them are not connected or used. I will initialize all pins in a single function called io.init. And I decided to store the configuration for all pins in an array using the pin names as indexes and the struct io.config as values. So kind of like a map between pin name and pin configuration. I can then loop through this array inside io.init and call io.configure on each pin. Simple enough. And then it was just a matter of filling this array with the correct configuration for each pin, starting with the pin for the test LED. This should be a GPIO pin, configure as output since it will be driving the LED, and it should be off by default. So I set select to GPIO, disable the resistor, it doesn't apply since it's an output pin, set the direction to output and output level to low. Then there are the transmit and receive pins for the UART. These are straightforward, they should be connected to the UART peripheral, so the only thing that needs to be set is the select register. The rest of the registers don't apply in this case. And next there are several pins that are unused. These are important to consider because even if pins are unused or unconnected, it's good practice to give them an appropriate default configuration. The reason for this is mainly that unconfigured pins may be floating, and among other things, floating pins have unpredictable current consumption, as I explained before. The recommended configuration for unused pins will vary between microcontrollers, but it's usually mentioned in the datasheet. For MSP430, TI says that the pins should be configured as output or as input with a pull-up or pull-down resistor. I prefer input in this case since that reduces the chance of an accidental short circuit. And I use pull-down over pull-up for no particular reason, I don't think it really matters. And for now I let the pins on the launchpad be unused and I will assign them as I go along in the future videos. And since there are so many unused pins and I'm using the same configuration for each one, I decided to put it inside a define to avoid repeating myself so much. And continuing on with the pins on the PCB, next is the pin for the IO receiver. This pin needs to detect the logical input level to parse the signal from the IO receiver. And actually later on I will have an interrupt configured to be able to sense these changes quickly, but that's for a later video as well. As such, this needs to be a GPIO input pin, but I actually don't need a pull-up or pull-down resistor for this one, because there is already a resistor inside the IO receiver. So just selecting GPIO and input direction is enough for this pin. Then there are the two pins for I2C, one clock line and one data line. Similar to io.h, I2C is handled by a peripheral, so all I need to do is select the correct alternative function, which is alternative 3 for I2C on these pins. I think it's possible to enable the internal pull-ups here as well, but I have external pull-ups on my board, so that's not needed, and regardless, the internal resistor values are probably too large for I2C. Next are the control pins connected to the motor drivers. These control the direction of the motors. They need to be GPIO output pins. Resistors don't apply, and I'm setting them as output low by default. Basically the same configuration as for the test LED pin. Then there are two pins for the PWM signals, which control the speed of the motors. While there are no dedicated horror PWMs on MSP430, PWM can be realized with the timer peripheral, so that's what I'm doing. The timer peripheral is alternative function 1, so I set the select register to that. I must also configure the direction output here. This is one of those exceptions where you need to configure the GPIO aspect of the pin even when an alternative function is selected. The resistor and out register are not applicable. Next is the pin I use to detect when the range measurement is done on the front range sensor. When this pin goes low, I know that the measurement is done. Going over the datasheet a second time, I actually notice I made a mistake on my PCB here. This pin should actually have an external pull-up resistor, which it doesn't have on my PCB. It has worked fine anyway, but just to be safe, I changed my code to enable the internal pull-up resistor now. In other words, a GPIO input with internal pull-up resistor. Moving on. Next is another set of output pins. These are for the extra lines on the range sensors. I control these to set the range sensors in boot mode. I configure these the same way as the previous output pins as GPIO output and low by default. Finally, I have the ADC pins, which connect to the line detectors. These are a special case because for these pins you don't even need to select the function. Their function are completely overridden by the ADC peripheral, which I will configure in a later video. So for now I just leave them as floating input by default. Then to configure all pins in one go, I loop over the array and call io.configure on each value. I also added a define here to get the array size of an array. This divides the size of the array with the size of its element. Then I fixed any compile errors and made sure I could compile for both targets, the launchpad and the robot. Like now I have rushed through all of these pins very quickly, but don't worry, I will spend more time on them individually in the coming videos. It was again time to format, CPP check and commit. And then push. I quickly went through the commits to see that I hadn't missed anything before finally merging the pull request. There you go. A long video, but at last I got to write a bunch of code. I'm pretty satisfied with how this turned out. It took some time, but I was able to clean up and improve from the previous version of this code. This is of course not the only way to go about writing the IO handling for a microcontroller project. I mean, these days there are so much helper code, helper libraries and code generation tools that can help you out with all of this, so you don't have to write everything from scratch. But I still wouldn't be surprised to see many people writing their own IO handling, especially for smaller projects where you need to be more conscious about how you write your code. Overall, it's nice to have all of the IO handling in a single place, and I think it's worth spending some extra time on this because IO handling is such a fundamental part of a microcontroller project, and if you spend some extra time on it, you can reuse it across different projects. And this brings me on to another point I want to emphasize. What I've done here is by no means specific to the particular microcontroller I've been using here, the MSP430. Yes, the registers are obviously specific to this microcontroller, but the general approach can be applied to any microcontroller really. And that's kind of the point with the code abstractions I'm writing here, to separate the specifics of the hardware from the code that I interact with. So that's all for this video. See you in the next video.